So buffers, what they do is they resist pH change. With small amounts of, well, from, let's say, from small amounts of strong acid or base. So in other words, I could put, with a buffer, I can put a little bit of strong acid in, and those hydrogens will be absorbed by the buffer. And so the pH won't change very much. That's what a buffer does. So you identify a buffer because it contains the weak acid, contains weak acid and its conjugate's base. Or a weak base and its conjugate acid. The acid neutralizes the base. And the base neutralizes any added acid. So same thing, right? Okay. So which one of these is a buffer, would be set up for a buffer? Okay. So example, which is a good buffer? So this is a multiple choice question on the exam. Which one would be a good buffer? What do we think? Thoughts? 1, 2, 3, or 4? Okay, we ready? Hold up fingers. Ready? Go. Andrew? Okay, good. Paige, what do you think? Which one's going to be a good buffer? Okay. Well, I very much value answer 2. However, HNO3 is a strong acid and buffers are weak. So the answer is number 4, D. Okay, this is a weak acid, HNO3. HNO2 is a weak acid, and contrary, there is its salt, right? So there is its conjugate base. Okay? So, and that is a, which of the following is going to make the best buffer? There it is. That is a question on the test. All right. So here's the acid, and then here is the conjugate base. HNO2 is a weak acid. So what's wrong with this one? HNO3 is a strong acid. So no. So this is the answer. Okay? All right. Number 1 would not work. They're both acids. So number 1 would not work. Both acids. And number 3 will not work because they don't match. So it's not an acid and conjugate base pair. That's why. Okay? So you're looking for an acid and conjugate base pair. Meaning, like, this is the conjugate base, right? All right, questions? All right, let's keep going. So, for example, you would have HCO3 minus plus water is going to give you the H2CO3. And then that H2CO3 plus water is going to give you HCO3 minus plus H2O. So then this ion is going to go back up and absorb those hydrogen ions. So this is a buffer. This HCO3 ion is a buffer because it can do both. It can absorb these ions. It's going to create this weak acid, and here's the base. So it has the ability to absorb the positive ions, and then the weak acid will dissociate into the conjugate base. The conjugate base will absorb the ions, and then it'll dissociate again. It's because the weak acid can go back and forth. That's what allows this to happen. Okay, so now there's an equation that has to do with this. It's called the Henderson-Hasselbalch. I don't place a lot of power in this equation. However, there are people who swear by it. So I teach it, and some people are like, yeah, this is totally the bomb. I love this equation. In general, there's not a lot of calculating that people do with this. In general, it's about what you can do with the ratio that's in it without calculating, okay? So here is the equation. pH is equal to pKa plus the log of the conjugate base over the initial acid. Now, a couple things to know about this equation which make it super easy to use. I don't use it because I just don't think about it, I guess. So first, you're going to assume, when you use this, and then I'm going to show you how to use it, that the equilibrium concentrations of the acid and conjugate base equal the initial concentration. Oh, one more thing. It's really important to note that buffers are made by adding the weak acid and adding the conjugate base. The conjugate base is not produced. So for example, when you produce this buffer, you actually add the nitrous acid and you add the sodium nitrite. They are added together with a specific purpose of making the buffer, all right? And so you don't, like, this is not one reaction. In this reaction, this was like sodium hydrogen carbonate, which dissociated to produce the hydrogen carbonate, which then acts with the water to produce the acid. Then also, in addition, carbonic acid was added, which also produces this ion. So these were added together on purpose to do two different jobs. And because they're weak acids and weak bases, what they do is they switch places. Imagine that, so that you add the weak base, it takes on the hydrogens and becomes the weak acid. You add the weak acid, it takes on the you add the weak acid, it adds hydrogens in and becomes the weak base. So they like switch places back and forth constantly. But you have to add in each part of it, okay? All right, so assume that the equilibrium concentration of the acid and the conjugate base equal the initial concentrations. Why? Because they're so close to that to begin with. Because they're close to each other. The Ka and the BKBs are close. They're weak acid, weak base. They're both close to 10 to the minus 7. So it's close, right? Okay. Also, she says, okay, if the concentration, because you see this ratio, this is what we're looking at in the ratio. If the concentration of HA is equal to the concentration of A minus, then the pH is equal to the pKa. Well, that's kind of interesting because the log, remember that the log of 1 is equal to 0. So if these two are equal, then this equals 0 and the pH equals the pKa. All right? So if you have the Ka, right? If you have the Ka, then the pKa is equal to negative log of the Ka. So now you have the pH. So if you have the Ka and your concentrations are equal, then you have the pH of the solution. Now, knowing that, then what you're actually doing is you're looking to see, is this ratio less than 1 or is it greater than 1? Because if this ratio is less than 1, so that would mean that your concentration of A minus is less than the concentration of HA. So your fraction is now less than 1. Then your pH is less than your pKa, because if this is less than 1, the log of anything less than 1 is negative. So then you're going to be subtracting from your pKa. So your pH is less than your pKa. If your concentration of your HA is less than your concentration of your A minus, then your ratio is over 1. And the log of anything that's over 1 is positive. And so now your pH is going to be greater than pKa because you're adding two things together. So this generally is how the Henderson-Hasselbalch is used. Numbers are not generally put in, but you can, all right? Okay. So let's look at an example. So here's an example. Calculate the pH of the buffer solution. So here's the buffer solution. 0.20 molar benzoic acid and 0.10 molar sodium benzoate are dissolved in 1 liter of water. What is the pH? Okay, so first we're going to, the Ka for benzoate, benzoic acid, is equal to 6.3 times 10 to the minus 5. Okay, so the first thing that I did was I said, oh, well, I'm going to get the pKa then, right? So that's the first thing I did. I was like, well, since I'm finding the pH, I'm going to need the pKa, so I'm going to figure that out because that'll make me feel good. So I did that. The pKa was 4.20. So that was nice. I did that. Okay, next. Next, I laid out my formula, so I wanted to see what I needed. So I know that the pH is equal to the pKa plus the log of the concentration of the A minus over the concentration of the HA. Now, according to my rules, which are here, it says that I can assume that the equilibrium concentration of the acid and the conjugate base are equal to the initial concentrations. Okay? So here are my initial concentrations. So now my solution has become pH is equal to 4.20 plus the log of my conjugate base, 0.10, over my acid, 0.20. Now, first of all, right away, we can say, oh, it's less than 1, which means my log is going to be negative, right? My log is going to be negative, which means that my pH is going to be lower than 4.2. That I know. All right? I can tell that. But they asked for more. They asked for actually what the pH is. So I run this through. I do my pH. All right? I do my log, and I run my pH through, and what I get is my pH is equal to 4.2 minus 0.301. So plus, and this is my log here, negative 0.301. 3 point, yeah. So my pH is equal to 3.90. Questions? So, it had to be, so it had to be. So they gave me two compounds. They said calculate the pH of the buffer solution. This is benzoic acid, and this is benzoate with a sodium in front. So, yeah. Okay. All right, next, let's look at the problem that I gave you here. So a 1.2 NaOCl solution is prepared by dissolving sodium hypochlorite in distilled water. The hydrolysis reaction is here. Write the equilibrium. This is an actual AP question, free response question. Write the equilibrium expression for the hydrolysis reaction that occurs. So CI. Write the equilibrium constant equation. So basically KEQ, which is a regular K. So you're writing that. Okay, so that's 1 point. Let's take this baby home. Ready? All right, only aqueous and gases, no liquids and no solids. Products over reactants, right? Okay. C2. Calculate the value of the equilibrium constant at 298 Kelvin for the hydrolysis reaction. Okay, so in this case, you have a Kb over here. Well, you have a Ka for the HOCl, right? All right. And you have a starting molarity. Okay. Calculate the value of the equilibrium constant. So you're really looking for the Kb or the Ka, right? What is the value? The equilibrium constant is a generalized term for Kb, Ka, Kw, Kd, K whatever. The K is the equilibrium constant. So what one are we looking for here? Look at the equation. What are you looking for? I think we're looking for the Kb. This is a base right here, right? This is the base. And this is an acid right here, right? So the base and the water are creating the acid. Everybody okay with that? So we have the Ka, so how are we going to find the Kb for this? Right, 1.0 times 10. So we're going to say what we're looking for is the Kb for OCl minus, right? Which is going to be equal to Kw divided by the Ka for HOCl. Does this make sense? Which is equal to 1.0 times 10 to the minus 14th divided by 2.9 times 10 to the minus 8th. Does that make sense? So that gives me 3.4 times 10 to the minus 7. Don't be afraid of trying something, like looking at it and saying, like, okay, this looks like a base. Because the thing is, if you're afraid and you don't try it, you could be thinking the right thing. The questions, remember what I said, if you know it, the questions are not hard. So if you're staring at it and you're thinking, that seems too easy, you might be right.
Good afternoon. If I could
Okay?
come quick enough,
Try and
we
finish
close
this
out today.
tonight. That's what I want you to do. Try and finish this problem tonight. Do your best. Do what you think is best. All right? Go through and try and figure out everything you can. Wiggle your way through the equations you have.
White Sox is home at 7. And we also